Welcome to True Projects. In this video, we are going to explain about the project entitled as Credit Scoring Prediction using Deep Learning Models in the Financial Sector. So before getting into the video, let me give you the brief description about the project. The project focuses on leveraging advanced neural network techniques to access borrowers' credit worthiness with higher accuracy and efficiency. By analyzing large volumes of financial and behavioral data, deep learning models enhance risk assessment, reduce default rates, and support smarter leading decisions in modern financial institutions. Coming to the abstract, credit scoring prediction is essential in the financial sector because it helps banks and financial institutes evaluate whether a borrower is likely to repay a loan. Traditional statistical approaches such as logistic regression and linear models are often limited in handling complex nonlinear relationships present in large and diverse financial data sets. This project addresses these limitations by applying advanced deep learning techniques that can automatically learn intricate patterns from vast amount of structured and unstructured data. The proposed system is trained using historical financial records, customer demographic information, transaction behaviors, and past repayment histories to build a predictive model capable of accurately assessing credit risk. By leveraging neural networks, the model improves prediction accuracy, enhances reliability, and reduces the likelihood of loan defaults. Ultimately, this approach provides a scalable and data driven solution that supports financial institutions in making more informed, efficient, and fair leading decisions. Coming to the existing system, the existing credit scoring system in the financial sector is mainly based on traditional statistical and machine learning techniques such as logistic regression, decision tree, support vector mission, and basic ensemble methods. Many institutions also rely only on rule based scorecards designed using historical customer data and expert knowledge. These models are popular because they are easy to interrupt, computationally efficient, and relatively simple to implement. However, they have significant limitations when dealing with large scale, high dimensional, and complex financial data set. Traditional approaches often struggles to capture nonlinear relationship among variables such as income patterns, spending behavior, and repayment history, which can reduce prediction accuracy and increases the chance of misclassifying borrowers. Moreover, as financial data becomes more dynamic and diverse, this system finds it difficult to adapt quickly to changing market condition and evolving customer behavior, limiting their overall effectiveness in modern credit risk assessment. Coming to the proposed system or base paper work, the proposed system is a deep learning based credit scoring model developed to address the shortcomings of traditional statistical approaches. It leverages advanced neural network architectures such as artificial neural network, deep neural network, and in some cases, convolutional neural network or recurrent neural network to enhance feature extraction and pattern recognition from complex financial data. The system begins with comprehensive data pre-processing, including normalization, feature engineering, and handling of missing values to ensure accurate and reliable inputs. By using multiple hidden layers and nonlinear activation functions, the model can automatically learn interactive relationships among variables such as transaction behavior, repayment history, and customer demographics. This enables higher prediction accuracy, improved scalability for large data set, and better adaptability to change financial trends. Additionally, the proposed system reduces manual intervention, supports real-time credit risk assessment, and enhances decision-making efficiency, ultimately helping financial institutions minimize credit default risk. Coming to the data set, first we have credit risk data set. The credit risk dataset is available on Kaggle is a structured financial dataset designed to help and analyze borrower behavior and predict the probability of loan default. It includes approximate of 32,000 individual loan records, which each row representing a unique borrower and their loan details. The dataset combines demographic information, financial indicators, and loan specific attributes It also contains historical credit information such as previous default records or credit history length, which are critical factors in assessing credit worthiness. The key target variable, loan status, is a binary outcome indicating whether the borrower defaulted or successfully repaid the loan, making the dataset highly suitable for supervised machine learning classification task because it contains both numerical and categorical variables. It supports a wide range of data preprocessing, feature engineering, and predictive modeling techniques. This dataset is commonly used in credit risk modeling, exploratory data analysis, financial risk assessment, and the development of decision support systems that assist financial institutions in minimizing lending risk and improving loan approval strategies. Next, we have AG News dataset. The AG News dataset is a widely recognized benchmark dataset used for multi-class text classification, especially in news topic categorization tasks. It consists of news articles categorized into four balanced classes: world, sports, business, and science or technology. The dataset is typically distributed into two files: train.csv and test.csv, with approximately 1,20,000 training samples and 7,600 testing samples. Each record includes a news title, a short description, and a numerical label ranking from 1 to 4, representing the category. Because of its balanced class distribution and clean structure, AG News is highly suitable for training and evaluating machine learning and deep learning models, making it a standard benchmark for comparing text classification performance. Next, we have SCI HTC dataset. The SCI HTC stands for Scientific Hierarchical Text Classification. Dataset is designed for hierarchical multi-label classification of scientific research papers. It contains titles and abstracts of overall 186,000 research articles, where each document may belongs to multiple categories organized within the hierarchical taxonomy. The dataset includes approximately 1,233 categories derived from structured classification systems such as the ACM computing classification system. Unlike flat classification datasets, SCI HTC requires models not only to assign multiple labels to each document but also to respect the hierarchical relationship among categories. This added complexity makes it particularly useful for advanced natural language processing research, especially in hierarchical and multi-label learning scenarios. And next we have UTCD dataset. The UTCD stands for Universal Text Classification Dataset, available on Hugging Face as Clarity Label Score. UTCD is a large-scale benchmark collection created to evaluate general-purpose and zero-shot text classification models. Rather than being a single dataset, UTCD integrates 18 different text classification datasets spanning multiple domains, including sentiment analysis, topic classification, intent detection, and emotion recognition. It contains millions of labeled examples with predefined training and testing splits. Each entry includes the text, corresponding labels, and metadata specifying its source dataset. UTCD is especially valuable for accessing a model's ability to generalize across diverse tasks and domains without requiring task-specific fine-tuning, making it ideal for evaluating robust and adaptable NLP systems. Coming to the novelty or extension or enhancement or improvement. First, as an extension to the base model, advanced contextual text representation were generated using Electra embeddings. Electra, a transformer-based language model, produces high-quality contextualized word embeddings that capture deep semantic and synthetic relationship within textual data. By leveraging these embeddings, the system improves feature representation for text-based inputs, leading to enhanced classification performance. In parallel, from numerical features, an ensemble voting classifier was constructed by combining predictions from multiple machine learning models. This ensemble approach reduces model bias and variance by aggregating outputs resulting in more stable and accurate predictions. Compared to previously proposed individual models, this hybrid extension demonstrates superior overall performance due to improved feature extraction and robust decision aggregation. Additionally, to enhance transparency and interpretability, explainable AI techniques were integrated into the system, especially LIME and SHAP. These techniques help explain how individual feature contributes to a model's prediction. LIME provides local explanations by approximating the models around a specific prediction, while SHAP calculates feature important values based on corporative game theory. By incorporating these models, the system offers clear insights into which textual or numerical features influence the final decision. This significantly improves trust, accountability, and transparency, which is especially important in sensitive domains such as finance or healthcare, where understanding the reason behind prediction is crucial for informed decision making. Furthermore, to make the system practical and user friendly, the Flask web framework was used to develop an interactive user interface. The UI allows users to input numerical and textual data for real time prediction using the trained deep learning and ensemble models. Additionally, the system supports topic modeling for textual data using the trained models from the dataset, enabling automatic identification of relevant topics from user provided text by deploying the solution through Flask. The project ensures accessibility, scalability, and ease of integration into real world application, bridging the gap between advanced machine learning models and the end user interaction. Coming to the flow of the work, as we are dealing with two different data sets like text data sets and numeric data sets, first let us check the flow for text data sets. In text data sets, first we have importing the packages. This module initializes all required libraries for data handling, pre-processing, visualization, modeling, and evaluation. Libraries like Pandas, NumPy, Scikit-learn, and Transformers are imported. Deep learning frameworks such as TensorFlow or PyTorch are also loaded. This step prepares the environment for text classification tasks. Next, load the datasets. The AG News datasets and SCI/HTC datasets are loaded from CSV files, while UTCD is loaded using the Hugging Face library. The text and target columns are identified. The datasets are inspected from structured and size before pre-processing. Next, pre-processing. Raw text is cleaned by removing URLs, mentions, hashtags, emojis, and punctuations. All text is converted to lowercase from consistency. Class labels are mapped properly. This ensures structured and noise-free input for modeling. Next, data visualization. Class distribution plots are generated to check dataset balance. Text length analysis helps determine padding size. Word clouds are created to identify frequently occurring words. These insights guide modeling decisions. Next, encoding. Text labels are converted into numerical format using label encoding. For deep learning models, one hot encoding is applied. This ensures compatibility between model outputs and target labels. Next, train test split. The dataset is divided into training and testing sets, usually in a 80 to 20% ratio. The training set is used for learning patterns, and the testing set evaluates generalization performance. Next, embedding layers. Pre-trained models like BERT, Robot A, and Electra are used to generate contextual embeddings. Text is tokenized and converted into dense vector representations. These embedding capture semantic meaning. Next, build the model. Multiple models such as BERT, BiLSTM, TextCNN, Fast Text Transformer, and hybrid loss plus LSTM models are implemented. Each model learns textual patterns differently. Their performance are compared to identify the best approach. Next, evaluation. Models are evaluated using accuracy, precision, recall, F1 score, and AUC. A classification report and confusion matrix are generated. This helps analyze prediction quality per class. Next, save the model. The trained models are saved using joblib, pickle, and model.save methods. Transformer models are saved using Hugging Face utilities. These saved models are later used in deployment. Next, metrics comparison. Performance metrics of all models are compared numerically in tables. Visual comparisons are done using bar charts and ROC curves. This identifies the best performing model. Next, explainable AI like Line and SHAP. Line explains individual predictions by highlighting important words. SHAP provides both global and local feature importance. This improves transparency and model trust. Now, coming to the numerical credit risk dataset workflow, in this, first we have importing the packages. Essential libraries such as Pandas, NumPy, Scikit-learn, XGBoost, LightGBM, and IMBlearn are imported. Visualization libraries are also included. This sets up the environment for tabular data modeling. And next we have load the data set. The credit risk data set is loaded into a data frame. The target variables is identified. Data structured and class distributions are examined. Next, pre-processing. Missing values are handled and duplicate records are removed. Data inconsistencies and outliers are treated if required. This ensures clean and reliable input data. Next, data visualization. Class distribution plots show imbalance between risky and non-risky borrowers. A correlation matrix identifies relationship between numerical features. These insights support feature selection. Next, encoding. Categorical features are converted into numerical form using label or one-hot encoding. The target variable is also encoded. This prepares the dataset from machine learning models. Next, feature selection. Recursive feature elimination selects the most important features. This reduces dimensionality and improves model efficiency. It also removes redundant variables. Next, oversampling. Smart generates synthetic samples for the minority class. This balances the dataset and prevents biased prediction. Oversampling is applied only to trained data. Next, training test split. The dataset is divided into training and testing subsets. The training set is used to build models. The testing set evaluates the performance. Next, build the models. Models such as logistic regression, random forest, XGBoost, LightGBM, hybrid LSTM model, and voting classifiers are trained. Each predicts borrower's risk status. Their performance are compared. Next, evaluation. Models are evaluated using accuracy, precision, recall, F1 score, and AUC score. Confusion matrix are generated. This ensures reliable financial risk prediction. Next, save the model. The best performing model is saved using JobLib or Pickle. This allows reuse during deployment. Next, metrics comparison. All models are compared numerically and visually using performance tables and ROC curves. This highlights the most effective algorithm. Next, explainable AI, Line and SHAP. Line explains individual credit decision locally. SHAP identifies globally important features such as income and loan amount. This ensures transparency and regulatory compliance. Coming to the front end, the front end is built using Flask with SQLite for storing user credentials. It supports user registration and login. This ensures secure access to the system. Users provide either text input for classification or numerical values for credit risk prediction. The form collects the validates user inputs. The system prepares the input for processing. User inputs are pre-processed using the same steps applied during training. Text is clean and tokenized while numerical features are scaled and encoded. This ensures prediction consistency. The saved trained model is loaded into the backend. The processed input is passed to the model. The model returns the prediction class and probability. The front end displays the prediction results and confidence score. For text data, topic modeling extracts top keywords. Important influencing features may also be shown for better interpretability. The algorithms used are for text dataset we used birth by LSTM, text CNN, fast text transformer, robot A, and proposed model includes hybrid loss plus LSTM and extinction we have used Electra. For numerical credit risk dataset we use logistic regression, random forest, XGBoost, Light GBM. Proposed model is hybrid loss plus LSTM and extension we have used voting classifier. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute the project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Model files. These are the model files which contain the algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows the users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, first, you need to copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Use the command cd followed by a space and paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome, so that the home page of the project should now be displayed in the browser. This is a front end built using the Flask framework. In this page, we have home button and sign up button. Firstly, click on sign up button so that create an account form will be opened where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on sign up so that all the given details are stored in signup.db and login.html will be opened where you need to access the application with the help of username and password. Click on sign in so that the prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button, and sign out button. Firstly, click on prediction button. As we are dealing with credit risk dataset and text classification datasets, now let us check one by one. First, click on credit score so that the prediction page will be displayed where you need to enter the credit score prediction values like person age, person income, house ownership, employment length, loan intent, loan grade, loan amount, loan interest rate, loan percent of income, credit history length. Let us enter the input values and check the prediction. The values are successfully entered. Now click on predict button so that the input values are pre-processed and the prediction results are good credit score. The confidence level is 82.12%. And here we have some recommendations like maintain timely repayments, keep credit utilization low, explore better financial opportunities. And we also have some precautions to be followed. Again, let us check the credit score for other details. Again, the values are being entered. Now click on predict so that the input values are pre-processed and the prediction results are bad credit score. The confidence level is 100%. Here we have the recommendations like improve repayment discipline, reduce credit dependencies, build a positive credit history, and we also have the precautions to be followed. Now let us check with text classification. When you click on text classification, the text classification prediction form will be open where you need to enter and choose a classification model to get the prediction. Firstly, we need to enter the text here and then click on the classification models to get predictions. First, let us give the input. The input has been successfully entered. Click on news classification and then predict text category so that the given input is pre-processed and the prediction is resulted as model prediction summary. It is a news model. The input text which we have given is given here. The predicted category is business. Prediction confidence is 98.83% based on the keywords detected. Now click on try another text. The text has been successfully entered. Select scientific text and click on predict text category so that the input text is pre-processed and the prediction is displayed as SCI HTC model. The input text is given here. Predicted category is biology and medicine. The prediction confidence is 98.04% based on the important keywords detected. And again, click on try another text. The text has been entered and click on UTCD classification and then click on predict text category so that the input text is pre-processed and the prediction has been resulted to UTCD model. Input text is displayed. The predicted category is intent. The confidence level is of 100% based on the important keywords detected. And then next click on graphs button so that all the four data sets graph will be displayed. Let us check one by one. First, let us check with credit risk graphs. In this, first we have class distribution graph. This graph shows the number of applicants classified as good credit score and bad credit score. It highlights dataset imbalance where one class may significantly outnumber two other. Such imbalance affects model training and justifies the use of ensemble and deep learning approaches for better risk prediction. Next, we have confusion matrix and ROC graph. The confusion matrix displays correctly and incorrectly predictions for good and bad credit classes, including false approvals and false rejections. The ROC curve illustrates the trade-off between true positive rates and false positive rates. Ensemble models like Oetting and XGBoost show fewer misclassifications and stronger overall discrimination. Next, we have accuracy graph. Accuracy represents the overall percentage of correctly classified applicants. The Oetting model achieves the highest accuracy, followed closely by LightGBM and XGBoost. This indicates strong overall predictive performance across both credit classes. Next, we have precision graph. Precision measures how mainly applicants predicted as good credit score are actually good. Higher precision, as seen in the Oetting model, reduces the risk of approving unreliable borrowers. It is crucial for minimizing financial losses due to incorrect approvals. Next, we have recall graph. Recall evaluates how effectively the model identifies bad credit score applicants. High recall values, particularly in Oetting and LightGBM, reduces the chance of approving high-risk customers. This metric is essential for effective credit risk management. Next, we have F1 score graph. The F1 score balances precision and recall into a single performance matrix. A high F1 score such as 95.7% for the Oetting model indicates consistent and reliable performance. It is especially important for imbalanced credit data sets. And next we have AUC graph. AUC stands for area under the ROC curve. It measures the model's ability to distinguish between good and bad credit scores across different thresholds. The Oetting model achieves the highest AUC, showing excellent classification capability. Higher AUC values indicates better overall separability between classes. And next we have explainable AI SHAP graph. SHAP explains how each feature contributes to the model's credit decision. It helps identify why an applicant is classified as good or bad credit. This improves transparency, supports regular complaints, and builds trust in AI-based credit score system. And next, let us check with news dataset graphs. In this first, we have class distribution graph. This graph shows how news articles are distributed across the four categories: world, sports, business, and SCI tech. It helps identify whether the dataset is balanced or if certain categories dominate. Class imbalance can influence model performance and justifies the use of transformer-based deep learning models. Next, we have confusion matrix graph. The confusion matrix presents the number of correct and incorrect predictions for each news category. It highlights where models confuse similar classes such as business and world. Transformer models like Electra Extension and Robot A shows fewer misclassifications indicating strong contextual understanding. Next, we have accuracy graph. Accuracy measures the overall percentage of correctly classified news articles. The Electra extension model achieves the highest accuracy, followed by Robot A and BERT. This reflects the effectiveness of transformer architectures in multi-class text classification. Next, we have precision graph. Precision indicates how many articles predicted under a specific category truly belong to that category. High precision, especially from Electra extinction, reduces false positive across classes. Transformer models consistently outperform CNN and RNN models in maintaining prediction correctness. Next, we have recall graph. Recall evaluates the model's ability to correctly identify all articles belonging to each category. High recall values ensure that fewer relevant articles are missed during classification. Transformer models demonstrate strong topic convergence with minimal mispredictions. Next, we have F1 score graph. The F1 score balances precision and recall into a single metric for overall performance evaluation. A high F1 score such as 96.1% for Electra extension indicates consistent and reliable classification across all categories. It is especially useful for evaluating multi-class data sets. And next we have AUC comparison graph. AUC measures how well the model distinguishes between multiple news categories across decision threshold. The Electra extension models achieve the highest AUC, showing excellent discriminative ability. Higher AUC values reflect stronger separation between the classes. Next, we have explainable AI SHAP graph. SHAP explains how individual words and phrases influence the model's classification decision. It shows why an article is labeled as world, sports, business, or SCI tech. This improves transparency, builds trust, and supports accountability in automated news classification systems. Next, we have SCI HTC graphs. In this first, we have class distribution graph. This graph shows how scientific documents are distributed across biology and medicine, computer science, mathematics, physics, and other sciences. It highlights any class imbalance that may exist between search domains. Such imbalance can impact model learning and classification performance. Next, we have confusion matrix graph. The confusion matrix displays correct and incorrect predictions for each scientific category. It shows where models misclassify documents between related domains. Extinction Electra demonstrate the fewer errors, indicating stronger contextual understanding than CNN, RNN, and baseline transformers. Next, we have accuracy graph. Accuracy represents the overall percentage of correctly classified scientific documents. Extinction Electra achieves the highest accuracy, significantly outperforming Robot A and BERT. This reflects its superior capability in multi-domain scholarity text classification. Next, we have precision comparison graph. Precision measures how many documents predicted in a specific scientific domain are actually correct. Extinction Electra achieves the highest precision, reducing false positive classification. This is especially important for distinguishing between closely related academic fields. Next, we have recall graph. Recall evaluates how effectively the model identifies all documents belonging to each scientific category. Extinction Electra shows stronger coverage across domains, minimizing missed classifications. High recall ensures comprehensive topic detection. Next, we have F1 score comparison graph. The F1 score balances precision and recall into a single performance matrix. Extinction Electra achieves the highest F1 score, demonstrating stable and reliable classification performance. It confirms consistency, effectiveness across all research domains. Next, we have AUC graph. AUC measures the model's ability to distinguish between different scientific categories across decision thresholds. Extinction Electra achieves the highest, indicating excellent discriminative power. Higher AUC values reflect stronger separation between academic domains. Next, we have Explainable AI SHAP graph. SHAP explains the model's prediction by identifying key scientific terms and phrases influencing classification decision. It clarifies why a document is assigned to a specific research field. This improves transparency, interpretability, and trust in deep learning based classifiers. And next, let us check with UTCD graphs. In this first, we have class distribution graph. This graph shows how text samples are distributed across the three classes: intent, sentiment, and topic. It helps determine whether the dataset is balanced across tasks. A well-balanced distribution supports stable and effective multitask model training. Next, we have confusion matrix graph. The confusion matrix presents correct and incorrect predictions among intent, sentiment, and topic classes. It highlights areas where the model may confuse similar labels. Extinction Electra and Robot A shows minimal misclassifications, indicating strong contextual understanding. Next, we have accuracy graph. Accuracy measures the overall percentage of correctly classified text samples across all tasks. Extinction Electra achieves the highest accuracy, outperforming Robot A and BERT. This demonstrates excellent generalization and multitask learning capability. Next, we have precision graph. Precision indicates how many predicted labels are actually correct. Extinction Electra achieves the highest precision, significantly reduces false positives. High precision ensures reliable classification outputs. Next, we have a recall graph. Recall evaluates the model's ability to correctly identify all relevant instances of each classes. Extinction Electra achieves very high recall, meaning very few samples are missed. This ensures comprehensive detection across tasks. Next, we have F1 score graph. The F1 score balances precision and recall into a single matrix. Extinction Electra records the highest F1 score, confirming consistent and stable performance. It reflects strong effectiveness in multitask text classification. Next, we have AUC graph. AUC measures how well the model distinguishes between different text classes across decision thresholds. Extinction Electra achieves a perfect AUC of 100%, showing exceptional discriminative ability. This indicates clear separation among intent, sentiment, and topic categories. Next, we have Explainable AI SHAP graph. SHAP explains model prediction by identifying keywords that influence intent, sentiment, and topic decisions. It provides insights into how the model makes classification. This improves transparency, interpretability, and trust in transformer-based system. And finally, click on Sign Out. So, this project demonstrates that deep learning and ensemble models significantly enhance credit score prediction in the financial sector. Advanced models such as hybrid LSTM and ensemble techniques improve risk discrimination, reduces false approvals, and strengthen decision reliability. The integration of performance metrics and explainable AI ensures both high predictive accuracy and regulatory transparency. Overall, the proposed approach supports more secure, data-driven, and trustworthy credit risk assessment system. This is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.